Hi everyone, it's Mr. Krieger. We're going to be doing the next lesson, lesson 4 of Unit 10 on circles. How do we solve circle problems with right triangles? And the right triangles will be created, of course, by lines that are in or around the circle. So let's take a look at the first scenario. Okay, so just keep in mind, up until now we've been exploring angles and arcs formed by the segments in the circle. Now we'll look at the lengths of these line segments. We've been talking about the relationship between angles and arcs. Now we're going to be talking about how long these line segments are. So that's the idea of this lesson. Okay, so here's the first concept. Triangle created by a radius and a tangent. So you have a radius and a tangent and you connect, let's say this comes to an endpoint and you connect the center of the circle to that endpoint. This is going to be a right triangle. And let me show you where the right angle is going to be. The right angle is going to be where the radius and the tangent meet right there. Now, it may look to you like that angle in there by O is a right angle, but that's not where the right angle is. The right angle is up by where the radius and the tangent meet right on the circle. And again, if you draw your circle really quickly, it might actually seem like the right angle is in the center, but it's not. Just keep that in mind. It's the most important thing. Now, why is this relationship true? Why is that a right angle? This follows from something we learned in the last lesson, and that is when a chord and a tangent meet, the angle is 1/2 the intercepted arc. So let's take a look. Here we have a radius, which is not a chord. But if you were to extend this radius the full way, that creates a diameter. And a diameter is a type of chord, right? And now let's put the tangent line in so it touches the diameter right there. Oh, let's think about this. This arc right here is half a circle because the diameter cuts a circle in half. That's a 180-degree arc. And what we know is that the angle is 1/2 the intercepted arc. So that makes this angle 90 degrees, where the tangent and the diameter or radius touch the circle. By the circle is where the right angle will be, okay? Okay, what are the facts about the diagram? Okay, examples of radii. Well, OC is a radii, and OA is a radii, a radius, I should say, and it's important to keep in mind that there are 2 radiuses in this circle, because you're going to see some particular examples coming up where that's important to know. Okay, tangent AB is the only tangent that goes through point A, the only tangent that's drawn. There can only be one tangent on a circle at a specific point. If a line is tangent to a circle, then it is perpendicular to a radius at a point on the circle. Here, OA is perpendicular to AB. OA is perpendicular to AB, which makes angle OAB a right angle, and therefore triangle OAB is a right triangle. Okay, so let's try a couple of problems out so you can see how this will work, and you should be fine with this stuff because this is like a review of stuff we've done before. Okay, in the diagram, the radius is 8 centimeters and the tangent segment is 15 centimeters, okay? But here's a hint, always draw in the right angle by the tangent. So over here, that's where the right angle is going to be. Now let's label the sides with the appropriate numbers. The radius is 8, so I'll put an 8 by OA. The tangent segment is 15. And we want to find the length of the segment OB. So this segment over here, I'll call it X. Well, it's a right triangle. You know what to do if you have a right triangle and you know 2 of the 3 sides. You wouldn't use trigonometry here. You would just go back to the Pythagorean Theorem. All right, where 8 and 15 are the legs, and this side, OB, that's the hypotenuse. So you're going to have 8 squared plus 15 squared equals X squared. You get 64 plus 225 is X squared. This becomes 289. And you get X equals 17. So segment OB is 17 units. Okay? So it's just simple Pythagorean theorem as long as you know where the right angle is. Okay, follow-up question. What is the length of segment CB? I'll put a little y here from C to B. Well, this is using this fact that we were talking about before, that not only is OA a tangent, but OC is a tangent. That part's 8. So since OB is 17 and OC is 8, if we subtract those, then CB is going to be 9 units. 17 minus 8 is 9. Okay, so it's going to be important for you to keep that in mind. All right, let's go take a look at some more of these types of problems. All right, you could probably try the next one on your own. If you have any trouble with it, you can, let me show you what to do. But I'll read it, and if you want to pause it and try it, go ahead. In the diagram, suppose the radius is 7 and the tangent segment is 12. So the tangent segment is 12 and the radius is 7, and draw in that right angle by point A. What is the length of segment OB? Okay, again, this is straightforward, just like we had done before. It's going to be the Pythagorean Theorem. 7 squared plus 12 squared equals x squared. 49 plus 144 equals x squared. So you get 193 is x squared. And so it asks for us to round this to the nearest tenth. So the square root of 193 is 13.892, ... So to the nearest tenth, it's going to be 13.9. So OB is 13.9. And then there was a follow-up question, what about segment CB? You should be good with that now. It's going to be 13.9 minus what? Since OC is 7, we can subtract those, and we get that 6.9. So that's going to be CB. All right? Okay, let's take a look at the next problem. All right, this one, it's not particularly more difficult, but there's one small trick in it. Let's take a look what it says. In the diagram below, OR is the radius and RS is a tangent. If TS is 14 and OR is 5, what is the length of tangent RS? Let's put the right angle where it belongs. It's not by O, it's by R. Now, the 14 is not from O to S. The 14 is from T to S, so please keep that in mind. Well, how long is it from O to S? Well, OT is 5, so therefore OS is 19. So now when you're going to use the Pythagorean Theorem here, you have to use, this is your C value, so it's going to be like 5 squared for the OR part plus x squared for the RS part equals 19 squared for the OS part. Okay, so what do we get here? We get 25 plus x squared equals 361. Subtract 25 on both sides, and that gives you 336. And it's asking us to put the answer in simplest radical form. Let's think about how we do that. Remember, you want to look at your perfect squares. The perfect squares are like, 4, 9, 16. I'll put them over here. Remember, 2 squared is 4, 3 squared is 9, 4 squared is 16, 5 squared is 25, etc. What number goes evenly into 336 from this list? 16 is the largest such number. 16 times 21. Give them their own radicals, and you get 4 rad 21 is the length of RS in simplest radical form. Okay, so that's how you do those problems. All right, let's take a look at another scenario. Okay, so take a look at this situation here, and it's just like the same exact thing we've been doing, except now we've drawn in a second triangle on the other half of the circle. All right, so let's label some of the things. Let's draw in where the right angles are. Where do you think the right angles are? They're not by O, they're by P and by R. Okay, which segments are the tangent segments? This one here is a tangent segment, and this one here is a tangent segment. This thing here is not a tangent, it goes into the circle, okay? What are the radii? So there's a radius over here, I'll just call it R for radius. There's a radius over here, okay? What would be the hypotenuse in a triangle here? The hypotenuse is going to be that OQ. So I'll put a hype over there. This is the hypotenuse, okay? So Just keep that in mind. Oh, and so C is going to be OQ. So O to Q is going to be your hypotenuse in this scenario. So it's really the same thing. It's just now there's a double triangle there. All right, let's try some problems with that. Okay, so here's what we got. In the diagram below, OP and OR are radii, QR and QP are tangents. If OQ is 40, it's going to be a little hard to label. That's this whole thing down the middle is 40. PQ is 35. Then what is the measure of the radius? So I'm going to put the 40 here. That's the whole part OQ. Let's keep in mind where our right angle is. There's a right angle over here. And we want to find the measure of the radius. So I'll put an X right over here. And again, in simplest radical form. So again, we're going to use the Pythagorean Theorem here. And we're going to remember this is our C, that line from O to Q. That's across from the right angle. So that's going to be here. So we're going to get x squared plus 35 squared equals 40 squared. X squared plus 1,225 equals 1,600 minus 1,225. And we get x squared equals 375. And if we're going to simplify this radical, we're going to need those perfect squares again. 25 is a perfect square that goes into 375, and it goes in 15 times. So what you're going to get is 5 rad 15. So that's the measure of the radius, or OP. Now it says, what's the measure of RQ? Oh, that's something new. What do you think it's going to be? Well, since the radius is going to be the same here and here, and since this piece is the hypotenuse, then shouldn't this piece be the same as this? Shouldn't it be 35? We're going to take a look at that in a minute, but it is going to be 35. And again, it's a symmetrical thing. If you just used Pythagorean, since we know all radii of a circle are equal, if we put the 5 rad 15 here and did the Pythagorean theorem, this is definitely going to be 35. But let's take a look at that in a little bit. Let's do a little summary here. Okay, what type of angle is formed in each of these diagrams? Well, remember, we say when a radius and a tangent meet, they make right angles. Here, the right angles are in those locations, so these are the right angles. For both diagrams above, what formula would you use? Remember, because they're right triangles, you use the Pythagorean theorem. Which sides are the hypotenuse in the diagrams above? LO is going to be the hypotenuse for this diagram, and OQ is going to be the hypotenuse for this diagram. And since you all know how to use the Pythagorean theorem, you should be good with this. All right, we're going to take a look at the next thing. All right, so now you might think this is a little bit of a silly diagram, but again, it's a little way to help you to remember the fact in the diagram that we're going to see. Okay, what is the relationship between the lengths of two tangents meeting at the same external point? Now, we're not doing the arcs here. We've seen a similar scenario when we were talking about the arcs and the angle. We're not talking about the arcs and the angle. We're talking about the lengths. So here's the fact. When two tangents of a circle meet at the same external point, like P over here, the lengths are equal. The lengths are going to be equal. Okay? I call this the party hat theorem because I see that those two sides, like the sides of a party hat, and these pieces are equal to each other. So in this case, PB is going to be 13 units. And that's what we saw. I'm going to come back here for a second. These were both 35. That's like the party hat theorem. So, and again, you could prove that these segments have to both be the same. Now you just know a shortcut that when you see two tangent lines from the same external point going to the circle, those two segments have to be equal. So now we're going to take a look at some examples. Now, you might not see in this problem what looks like an example of this, but there is. Let's take a look at how it works. In the diagram below, QM is 8, RN is 5, and LR is 7, and it wants to know the perimeter of the big triangle. You might say, what does this have to do with that? Well, let's take a look. If you look, and I'll use a different color here. That's the party hat right there. If this is 7, then this must be 7. Okay? Let's turn this around. That's like a party hat too. If this is 8, then this piece is going to be 8. So this piece is 8. And there's another party hat right there. If this piece is 5 from R to N, then S to N has to be 5. So therefore, your perimeter of your triangle is just literally 8 plus 7 plus 7 plus 5 plus 5 plus 8. You add those all together and you get the perimeter is 40. Okay, so these are 3 like little party hats on the same circle. All right, let's take a look at this problem. In the diagram below, QM is 5, LR is 6, and the perimeter of the triangle is 30, and they want you to find SN. See if you can think through this problem. It's a little different from this problem. This time, here they gave you enough information to fill in all these pieces. Here, all we know is that these pieces are equal. And I don't know what that piece is. It's X. These pieces are equal. That's helpful. That means that this is 6. These pieces are equal. That's helpful because this will be 5. And now, can you think of an equation that will work if all these have to add up to 30? So 5 plus 5 plus 6 plus 6 plus x equals 30. Combining everything that's like each other, that's going to be 22 plus 2x equals 30 minus 22 on both sides. 2x equals 8. And therefore x equals 4. Therefore Sn equals 4. Okay? So that's how you do a problem like this. Okay. Now, this is another new concept. It's pretty easy, and it's going to be similar to the first problem that we did. What is the distance between the center of a circle and a chord? Well, the first thing we want to talk about, because it's a related concept, is how do we measure the distance between a point and a line? Let's say you have a line and you have a point, right? And I want to know how far away this point is from this line. So look, I could pick a whole bunch of different points on this line and measure that distance. But I could pick that point, or I could pick this point, or I could pick a point way up there or way down here. And they're all going to have different lengths. But when we want to measure the length between a point and a line, what we want to do is, since there's a million different lengths you could choose from, there's only one shortest length, and we want the shortest distance. And the way you do that is you find a point that when you connect the point you're trying to find the length to the line with, and a point on the line, it will be the shortest distance, and it's going to be perpendicular to the line. So this point right here, the one that makes a line segment perpendicular, is the shortest distance. And when we talk about the distance between a point and a line, we're talking about that shortest distance. We're going to call it the perpendicular distance. Okay? So now we're going to see something similar. Okay, when you find the distance between the center of a circle and a chord, center of the circle is the point, like that point. The chord is like the line segment, like that. Okay, when you find the distance between the center of a circle and a chord, you create a perpendicular bisector. These two line segments are perpendicular to each other. They're creating right angles. And it's a bisector. SR and RT are going to be equal in length. This length and this length are equal. That's going to be very helpful to know. Okay, so here are some facts. Angles SRO and TRO are right angles. Also, SR is congruent to RT. SR and RT are congruent, all right? Now, let's take a look at a problem. If a chord that's going from here to here, I'll call it AB. So let's call it AB. If a chord is 6 inches long and the distance between the center of the circle and the chord is 4 inches, so there's going to be a 4 here, what's the length of the radius? What do you think the radius is here? There's no point here. Do you think it's A to this point? Do you think it's O to this point? Actually, there is no radius drawn in this diagram yet. You have to draw the radius in. Now, you could draw a million different radii in here, but there's only two that would be useful to us, either going from O to A or from O to B. Since I wrote that on that side, I'm going to go from O to B, but it doesn't matter if you go O to A or O to B or both. Now, it says that this chord here is 6 inches long from A to B. I want to go like this. That's 6 inches. This distance is 6 inches. But how long is it from here to here, from this middle point to that? That's got to be 3 inches. Remember, these segments are equal. So if this is 6, those are 3 and 3. Now, we go back to our Pythagorean theorem. We want to find this radius, which is like the hypotenuse of a right triangle. So we're going to do a squared plus b squared equals c squared. You're going to get 3 squared plus 4 squared equals plus x equals x squared. 9 plus 16 equals x squared. 25 equals x squared, and x equals 5. So the radius is 5. Okay, I think we're up to our last page here. Okay, so a couple of more problems. Let's take a look. This one doesn't have a diagram, so we're going to have to draw one. You could try to do it yourself, and if you have trouble, you can look at the video. Okay, if a chord, well, obviously I'm going to need a circle. Try to draw yourself a reasonable circle. If a chord is 10 inches long, that's 10 inches. And the distance between the center of the circle and the chord is 5 inches. So here's the center of the circle. And remember, if you're drawing the line segment to measure the distance from this point O to the chord, it has to make a right angle. That piece is 5 inches. What is the length of the radius? Again, we're going to have to draw in a radius here. And I'll put an x here. It's asking for the answer in simplest radical form. So the only problem is we have a 10 and a 5. Do we want to use the 10 and the 5 in our Pythagorean theorem? No. We want to make that 5 because these two are equal to each other. So now we're going to use the Pythagorean theorem. And we got 5 squared. This is the hypotenuse. So 5 squared plus 5 squared equals x squared. 25 plus 25 equals x squared. 50 equals x squared. And we can break that down. We're going to do simplest radical form. 25 and 2 are going to be the numbers you're going to use. So you get 5 rad 2. So the radius is 5 rad 2. Okay? All right. Let's take a look at our last problem. In the diagram below, if a chord is 30 inches long and the radius is 17 inches long, what is the distance between the center of the circle and the chord? I think you could figure this one out on your own. Pause the video, try it out. This is 30. The chord is 30, and the radius, this time they're giving you the radius, is 17. And they want you to figure out how long this distance is right here. We know there's a right angle over here. This is going to be 15. Do not use 30 in your Pythagorean theorem. The 30 goes beyond the triangle. The triangle is only this piece right here. So a squared plus b squared equals c squared. We're going to get x squared plus 15 squared equals 17 squared. So x squared plus 225 equals 289. Subtract off the 225 on both sides, and you get x squared equals 64. So it's going to be x equals 8. So the distance between O and that line segment is 8. Okay? So here are a couple of tips. Make sure you label everything with the appropriate numbers. Look for the radii. Make sure you put in the right angles where they belong. Look to see if you need to half the chord length. Remember, in these two problems, I gave you the whole chord. We don't want to use that whole number in our Pythagorean theorem. We just want to use the half. See if you need a piece of the chord or the full chord. So double the length of the piece if you need to. Okay, so good luck with the homework.